Our opening speaker today is Davide Santo, Radar Sensing Solutions General Manager at ON Semiconductor. His presentation is titled Securing Sensing, Why and How. He will briefly introduce the reasons that are leading more and more towards automotive secure sensors and give a high-level overview of a possible architecture approach on how to implement them for radar and imager. Davide, over to you.
Thank you. Good afternoon, everyone. So we're going to be speaking about sensing and security. Let's start with a high-level concept of why security in a sensor. The sensors are the eyes of the vehicle. Specifically, there will be more and more the eyes of and the ears of the vehicle that becomes autonomous. They do have an impact. Security has an impact, and therefore sensor with security has an impact on the consumer confidence, and they can prevent damages to the vehicle and to the reputation of the OEM. On top, legislations and standards exist that help us understanding how to introduce the security that already exists in automotive environment into the sensor, which is the last part where it has to be yet adapted. There are different modes of attacks today that are classified for security, and we will be talking specifically of a few of them during the course of the presentation. But let's go through them quickly just to refresh the language. Tampering is the attack where data is changed to add, remove, and modify objects in the view. And repudiation instead is the way that wrongly discarded data or data can be wrongly discarded even if maybe it was the correct data. Eavesdropping and privacy is very clear to everyone. It's capturing content for malicious purposes, listening to a private conversation. Spoofing instead is fooling the receiver into accepting data from an untrusted source, and denial of service clearly is the loss of, for example, a video or signals that can be important for driving the vehicles. A little bit of a trivia for interest and also to give a sense of security and the impact of it. How much time does it take today for an available computing power, for example, the Bitcoin miners level, to crack 90 bits key? Well, it takes only a few seconds. So security is effectively a problem. We need to protect our data, our privacy, our vehicles. But what will it take if the key is 128 bit? With today's computing capability, it's billions of years. And even if the Moore laws applies for the next hundreds or so here, it will take 78 years to get to 1 year times to decode. All of this to say that when we come to a sensor, when we come to implementing security inside a small object, we have to be very pragmatic in the choice that we will make, architecturally speaking, in the size of the keys, because they consume power, they consume time, and they become inefficient. So all of the presentation, we will try to focus on being pragmatic in an application of security at the sensor level. So as we say, the security and sensor is already being part of the industry. The crypto systems are already developed according to ISO standards. We need to maintain a flexible approach, so we want to provide a set of programmable crypto primitives that allows the customers of our sensor to have a security implementation as in an easier as possible way, and we want to be pragmatic or minimalistic. We want to reduce the resource requirements. So how are we going to protect and where we're going to focus in our approaches to adding security to sensing? We focus first of all on the protection of the physical sensor during the operation, of course, but also during the logistics, during the qualification phases, and during the audits that can happen. We want to protect, as a second part, the firmware. Firmware is where the customer, the end customer, the OEM, implements their own driving functions. We need to secure, therefore, the content through a secure boot. We want to secure the communication eventually. And that means that we will have to secure both the control data that controls the way a sensor behaves through vehicular networks or even private ones. And then effectively we might have to secure, and we'll have to secure, the physical data in itself. And one aspect that is always important when talking about security is essentially the key provisioning. 3 phases are expected in these cases. During development, there is no security applied. We need to be able to, or the customer needs to be able to use the sensor, test the sensor, and debug the sensor without having to apply security. Then there are 2 phases that are very relevant. A phase is during module productions, where through a secure room and a symmetric key provisioning systems, the customer can set up their own secure sensor to be shipped to the final OEMs. And then the asymmetric key provisioning, which can be instead the system that allows security to be applied onto the sensor or directly in the environments where the sensors are used. So let's talk about 2 classical and very famous sensors that populate today's vehicle. We will start with the radar, and then we will talk about the camera imaging. In radar today, the so-called radar ECUs are standalone systems. They have an internal sensor, which is sensing the RF signals, which is called an MMIC, and a microcontroller. And the entire authentication of the ECU, the protection of the customer firmware, and the implementation of the standard is done inside the microcontroller, which is locally connected, and therefore in an enclosed environment is quite secure and protected. But we can see, especially with a potential semi-autonomous and autonomous vehicle, the possibility to have more and more satellite sensors. A satellite sensor is a sensor that lives around the vehicle and connects through a cable into a central computing unit. In these cases, there is the need to add into the satellite sensor, into the physical MMIC, the same functions that allows authentications and firmware protection that was done before in the microcontroller. So the functions that we need to achieve into the radar sensor for satellite operations, for surround sensing, are essentially the securing of the ECU, the securing of the boot, and the securing of the communication. And there will be different approaches in the market, depending also on the different layers of the products that want to be presented to customers. And this approach can be more revolutionary and minimalistic and pragmatic, or more evolutionary. And in this sense, the difference can be really in the level of integration, where the revolutionary can be really small and could be used in sensor that might even be not connected to a constant source of energy, for example. On the evolutionary, instead, they can be developed through the experience already done through the microcontrollers that are present with security already in the vehicle environment. In any case, the accelerator for crypto hardware accelerator will have to cover a number of foundational points, from encryptions with different type of standards that needs to be applied, as you can see in the slide, to authentication using possibly pragmatic approach like CMAX, to the combination of the two, having a sufficient number of key stores and stored keys, and true number generation in order to have true secure procedure possible. On the imaging sensor, the same type of concept applies. Imaging is even more advanced than radar in adopting securities. There are already programs and products that has that. The imagers, of course, has the same type of problematics that any other secure sensor will have. We need to be sure that it's genuine, so it's not being, counterfeit, that there is an unmodified control. The imager is used for the purpose of what it was intentionally and is configured correctly, that the sensor data has not been corrupted and or modified. This is particularly true when we think of images that looks in front of the vehicle and will detect objects, cars, pedestrians, and other objects on the vehicle. System concept to understand why this is important is very clear. Imaging sensor can be used either directly connection to a host that can be local or remote, or they can even be connected to gateways, so they can even be routed and then rerouted to another internal location for computation. And in this system context, is relevant to understand why authentication becomes an important factor for imagers in the future. The risk to counterfeit or pirate components is a very serious concern for the automotive industry. The components that are of inferior quality but are sold as genuine parts have a major implication, of course, to the user of the vehicle, and even more to the manufacturer for the liability that this brings along. For vision system, the host needs to be able to verify that it's connected to a genuine imaging sensor. And it's important that a non-authentic sensor should never be trusted, and a suitable warning issues to the vehicle user. Then the tampering problem with the man-in-the-middle attack. The man-in-the-middle is a terminology used in security jargon to indicate that unit that can become the attacker, can destroy the content that the imaging sensor is sending to the final host. And these type of attacks can be of different levels and different types. Some cases are here represented. A man-in-the-middle can modify regions of the video from frame to hide information, so to hide the fact that there are more objects, that there is persons in the rooms or similar. He can replay previous video. It's already been proven that it's possible to replay the same street in the same weather condition without vehicles in front, and then the vehicle will not know that there is an object, an obstacle. It can delay video frames. It can read and write sensor registers without the host being aware, and therefore modify the behavior of the sensor, shutting it down, overexposing, or other type of behaviors. It can modify the register written by the host prior to the sensor receiving them, so it can really give a completely different setup. And it can modify on the other way the user data read by the host, so it can send completely wrong information to the host and therefore cause false behavior. So video tamper detection becomes a necessity and an important steps in the creation of a safer sensor. And the easiest way to do this is to append a message authentication code or a tag to the end of each video frame. So in principle, with a tag at the end of each video frame, the host uses the incoming video data to calculate his own authentication code and verifies by comparison that it is the same as the one for the incoming tag. If they match, the host can trust the integrity and the authenticity, of course, of the video frame, and can use the information, can elaborate based on the video frame, the information, and therefore the action that the vehicle will need to take. And the MAC is calculated cryptographically. An attacker can now modify the video data without the host detecting the modification. This is the foundational of tampering that needs to be applied to video and even to radar signal more and more. An example to complete this presentation is a possible architecture. This is a high-level representation of an architecture where it's visible how the crypto system or the crypto subsystem becomes a foundational element in the design of the sensor. As you can see, there is from the pixel array where there is the conversions essentially of the chroma value into a digital content. There is immediately the possibility to insert the crypto cell that will do the authentication with CMAC or GMAC type of authentication, with a control processor that locally controls the operations of the hardware security module before it's sent out to the host through a vehicle network or other type of connectivity point-to-point. From this point of view, again, the important things in sensor is to achieve a very high level of integrity from a security point of view, combined with the pragmatism of making security affordable from a power, size, and effectively even from a cost point of view. And with this, I complete my presentation, and thank you all for attention.